Hello students, in this video we have fourth illustration of chapter 6, a very interesting problem for understanding Lenz's law. In this video we are given three situations, and for each situation we are asked to determine direction of induced current. So this is first case, here is the second case, and third case. The question is, for each of this situation, we are asked to determine direction of induced current. So what is happening in first case? A square loop ABCD is brought in the magnetic field. In second case, triangular loop is taken out of magnetic field. In third case, irregular shaped loop is pushed out of magnetic field, and the blue crosses are indicating that field lines are going inside. So in which direction we will have induced EMF? So let us see how to determine direction of induced EMF. So we start with the first case. In first case, this is how magnetic field is established. Field lines are going inside, and in this field, suppose if I bring rectangular loop from one corner, this is the loop which we are bringing in. Okay, and the corners, let us label them as A, B, C, D. So what will happen as you drag it in this direction? So obviously the field lines passing through the loop will increase. Okay, and in that case, the situation is like, suppose here is a loop, and if you bring north pole close to it, you are increasing flux linked with the coil. And what can we expect in this situation? The expected nature of induced EMF is like this. The induced EMF should be in such a way that the field due to induced EMF opposes the change. What is the change? Change is that the external motion is increasing flux, and then only if induced magnetic field is like this, it can oppose the change. Okay, and hence the induced current must be like this. So here also this ABCD loop is brought in, and hence flux is increasing. So it must oppose the external magnetic field. Okay, so applying the right hand thumb rule, we realize that if current is like this, then only the side of the loop uh, facing us would become north pole. So direction of induced current should be A, B, C, D, A. If this is how current is induced, then only the outer part of the loop will behave like north pole, and inner side we have induced south pole, and then only it can oppose the external magnetic field. In second case, again the same magnetic field, but now the shape of loop is triangular. Does it make any difference? No. Shape of loop is not important, but how loop is moved is definitely of some importance. So this is the loop, and it is moved like this. Here is A, B, C. So as we drag the loop out, what do you think will happen to the flux? We know that flux will be reduced. So if flux is reduced, the condition is as if you are taking north pole away from it. Where is north pole? North pole is outside the screen, south pole is behind the screen, and the loop will feel as if north pole is taken away. Okay, and then the loop will try to induce current. It has to induce current actually in this fashion. Then you can say that the outside part of the loop will behave like south pole, and inside will behave like north pole, and then only it can control the decreasing flux. So in this case, the induction must be having the current nature from A to B to C to B. Now in third case, the shape of loop is some irregular, but as I said, shape of loop is not important. The nature of change in flux is important. So what we are doing, the irregular shaped loop is taken out. This is how we have the loop, and it is pushed out, and now we mark these points as A, B, C, D. So again, in this case, the flux linked with the loop will decrease if you take it out, and hence the loop will feel as if north pole is going away. So the part of the screen we are facing must induce south pole, and then the induced current has to be like this. Then only outside we have induced south pole, inside we have induced north pole. So what should be the nature of current in this case? The current must flow from A to B to C to D to A. So this should be the nature of induced current in these three cases. Thank you.